record. Okay. Yeah, and also I'm writing a Java book, so hopefully I will also come out with a good Java book. So for the future CS2 student, maybe
What is
benefit.
it about?
Pardon me, it's about Java. So Java object-oriented programming and all of the data structures. So I'm right. It's that's the amount of work. If you don't write a textbook, you don't know. Previously, I thought I can finish like this summer. Looks like no, I can only finish 1/5 my whole summer. It's too much of work because I need to come up with every single example myself and every single assignments. I need to make them up. I cannot copy paste. Yeah, it's too much of work. And also you need to find a way to, it's not like a lecture. You need to find some way to how to explain all of the concepts well. But hopefully when the book, when I finish it, will help a lot of students. Okay, anyway, I already started recording, yeah. So I will do share. Some student recommend push back the project. Push back the project a couple of days okay, but if push back next Sunday, then maybe some other assignments it can cause push back more. So I just want to get all of you guys' opinions about the coming project due this Sunday. Or we can have option like this. We still keep the due date as this coming Sunday, so that for those that still can make it, then you can make. And if you feel that like you have a lot of work, you cannot make it, then later you can send me email personally, and I can reopen the box for you to, or you can just send it to the later box. If you can make it due by next Wednesday, then we won't take any points off, so we won't give any penalty. Will this strategy good, meet all of you guys' demands, or you all think we need to push it back to next Wednesday? But I'm worried if I push back next Wednesday, then next week you will have more, because it's kind of like a snowball. It's rolling bigger and bigger for all of the piled assignments. So what's your opinion? Or just I will just do what I just said. So if some of you need more extension, then let's you just send me emails like next Wednesday. By next Wednesday you turn in, we won't take any points off. Is that good? Any recommendation?
On which assignment?
I don't know. Sarah said some project due this Sunday. I don't remember which project 2 or project 3.
Oh, it's the investment calculator. I mean, that probably works. Just sending an email if I have any problems, because we did FX last week.
Okay. So just let's just do that. Okay. So if you have personal needs, just let me know. Okay, no problem. Okay. So so then I won't update our course website for the due date. We just keep it like that. Okay. Let me start first. We are going to continue our discussion about recursion, okay, and recursion, yeah. And basically, we discussed recursive method in Java last class. So, okay, so then this is going to be our first quiz question for today. Okay, so what is a recursive method? So what is
a method that calls itself?
Very good. Yeah. So what is a recursive method? Very good. So you can send the answer as call a method, is it? Call itself, is it? That's a recursive method. And the call itself, then we need some special thing to deal with it so that you won't forever call yourself, is it? So a method call itself with what? With reduced case, is it? Is it with reduced case? Okay, so keep that in mind. Okay, so a recursive method, we said there are two conditions you need to put when you write a recursive method. One is it must have a stopping case. Is it? And the second is it must also have reduced case. Is it? Okay, so that's a recursive method we already know, is it? And then we also said compare recursive method versus iterative method. Which one is more efficient?
Iterative.
Yeah, very good. Iterative. Okay, that's the second quiz question. Okay, so compare recursive method and iterative method. Iterative method is more efficient. Why? The reason behind is what? Why it is iterative is more efficient?
Less
because
memory?
Not memory, because recursive, yeah, who said? Please, so a girl answer, is it? So who knows the reason why iterative is more efficient?
Well, because in our case, in iterative method, we use loop. We use just an int value. In case of recursive method, we use a recursion we call itself, and calling a method takes more memory than calling increasing a value.
Yeah, so the idea is we call that a concept as, let me write it here probably, okay, a method. So generally speaking, okay, in programming language, you call it a function. Function call overhead. Is it? Because for recursive call, you keep calling function, but each time you call a method, there is a call overhead. Why we say it's call overhead? Because you need to push the method to the stack. Is it? And then you also need to get it out of stack. Is it? So that's an overhead. Okay, we call it overhead, function call overhead, or method call overhead. Okay, so that's the reason. Okay, so if a method you can achieve it with iterative way, then write it in iterative way. Okay, don't write it as recursive method. Okay. But then over here, we mentioned method call. So method call has overhead, is it? then you may ask, then why do we need a method in programming language? Is it this is to do what? To do modularization. Modularization. So modular design, okay. So that's part of software design. You want your program be designed as module, as we call it divide and conquer. Is it a big task? Otherwise, you will have a huge main method. Is it so that's not going to be efficient? Is it? Of course, you can put all of the statements just in one method. Is it main method? But that's not a good design. Okay. So even though it has overhead, is it? It's we design some applications and we want to do modular design, as a divide and conquer, as it, and so that's why we still need a method, okay? Otherwise, you can have everything in main, is it? So that's not a good design. Okay, so that's just some review regarding recursive function, okay? So what today we will discuss is a new another example, okay? So this example is called binary search. Binary search, okay. And previously, I believe you all learned linear search. Linear search, okay, assuming for an array, okay, for a collection of items. Collection of items. Is it assuming like we have numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something. Is it? Okay, suppose you said, okay, I want to search. Assuming, let's just assuming we have 10 numbers, okay. We have 10 numbers. So I want to search 10. I want to know if 10 is in this array. Suppose this is an array. Okay, then what you need to do for linear search is you will do one by one comparison. One comparison. Is it? Until you do all the way. Is it? To the end, then you find the 10. You said, oh, I find it. Is it? Or you said, okay, I want to search -1. Then you need to go through all this array. Then you said, okay, I didn't find it. Is it? So for this array, it's small. It just has 10 items. Is it? It's a small array. This doesn't make some difference. You do exhaustive search. Is it? Every single one you are going to do comparison and you will make sure if it's there or not. Is it? And of course, if you said, oh, I want to search 1, that's very efficient. The first one you find it, then you don't need to continue. Is it? But a lot of time it will lead to exhaustive search. Is it? Every single one. Okay, and for small array or small collection array list, is it? It's not a big deal. Is it? But think about it. If you have 1 million or 1 billion items, and you are going to do this kind of exhaustive search, then it will take forever. Is it? That's why Google make a lot of money, because it has the best search algorithm for us. Is it? So this is regarding algorithm topic. Okay, but this is the simplest case. Okay, because Google, just think about when you do say one by one exhaustive search with million or billion items over the internet, the information for, of course, is it go to billions scale, is it? And if Google provide one by one comparison, is it may take a week to find a single item you want. Then do you want to use Google's service? Of course not, is it? And Google gave you back the result, just like in maybe in a second, is it? Very fast to give you back the result, is it? So here we can see when you do search, if we conducted this kind of linear search, it's kind of not that efficient, is it? Okay, then the idea is, can we find some good way to do search? Okay, so here is today's concept is, we have another way, we call it a binary search. There are all sorts of search algorithms, but this is one, definitely we will say it's better than linear, okay? Then linear one. Okay, so what's the idea? Let's see. So you have a sequence of items. Suppose in an array, okay, 6, then 7, 8, 9, 10. Suppose I have 10 items in an array. Is it in an array? But here for binary search, to be able to work, there is a precondition. Precondition is the items must be sorted. Be sorted already. Okay, it cannot be random numbers, random order. Okay, it must be sorted either in ascending or descending order. Okay, so in this case, it's ascending order. Descending order also fine, okay? So anyway, it's already sorted, is it? Okay, then let's see, suppose we still want to look for 10. Okay, so what's the idea? Okay, so the idea is you are going to look for the middle of the items. Okay, so what's the middle of the items? It's so it's the index. This is from sub-0, is it? And this is sub-9, is it? And so this middle one is sub-4. This is the middle one, middle item. Is it? Middle item. Okay, this is the item you are going to search. You're going to search. So I'm going to compare 10 with the middle one. Middle one is 5. Is it? And the 10 is greater than 5. Then just think about it. If 10 is greater than 5, do you need to worry from 1 to 4 and 5? Do we need to worry this range of items? Or we call this subset. Do we need to worry? We don't. Is it? Definitely 10 will not be in this subset. Is it? So you can drop it. You can drop this one, is it? So once we find the middle item, basically you can divide the original one to 2 subset, is it? The left subset and the right subset. right subset. And if the item you are going to look for is greater than the middle one, that means you can completely drop it. Drop the left subset, is it? Then you just keep the right part. Okay, we keep the right parts, then let's see. We keep the right part. Okay, then I have 9 here. Is it? Then in this sublist, this is sub-0. Is it? And this is 1, 2, 3, 4. This is sub-4. Is it? Then I'm going again to find the middle one. Middle one. Middle one is 2, sub-2. Is it? It's 8. Is it? So I'm going to compare 10 with 8. 10 is still greater than 8. And here we also then further divide the original list into the left one and the right one. Is it right one? And because 10 is greater than the middle one, so for sure you can drop the left one. Is it? I don't need to worry. Is it? I don't need to worry. So I will just keep the right one. Is it? Then for this right one, then for this right one, so you have sub-0, sub-1. Is it? And you find the middle one, so it's 9, is it? And you compare 10 with 9, it's greater than 9, is it? And it doesn't have left, so you drop it. So then you only have this single item and you find it. Is it? So totally, how many comparisons we did in this case? How many comparisons? We have the original 5, then we have 8, then we have 9, then we have 10. Is it total just 4 comparisons? Is it? Versus the original 10. Is it? It's decreased a lot. Is it? A lot. Then just think about if we apply this same approach, is it to like 1 million or 1 billion items, from sub-0 to the billion, is it? To the billion. And each time what you did, you find the middle one. The middle one. Is it? So 500 million. This is a position, okay, index. 500 million index. Is it you find? And you compare the item with the 500 million. Is it? So then you compare with this 500 million index. Index the item, is it array item? And if it is less than, if the item you want to look is less than this, then do you need to worry the other 500 million? The right 500 million? You don't, is it? So you see, then the first comparison, you already drop 500 million items. Is it 500 million item? And then you just need to worry this 500 million items. It's the same thing. And then you find the middle one. Then you compare, is it with the 250 million? Is it the middle item? And if it is greater than this new middle items. So how about let me use a different color. So you're going to compare with this new middle one, is it? So you're going to have, so here is $250 million. Here you have another $250 million. Okay, and suppose the item you want to search greater than this middle one, then you drop another $250 million. Is it $250 million? Then you just have a $250 million. Is it? So totally you already with two comparisons, we already drop 3/4 billion items. Is it to compare? And you keep doing this, is it? And each time you will shrink your search range by half. Is it by half? Then think about how efficient it is. Is it? Versus you need to conduct 1 billion times if the item is not there or if the item is at the very back. Is it? But of course, if the item is at the beginning, you just conduct a couple of comparisons. Is it? But that's very rare. Is it? So this is called binary search. Okay. So binary search. The idea is you find the middle item. They find the middle item in an array. Is it? And then compare search item with the middle one. Is it? If greater than middle one, then you drop left subset. Is it? And continue this same strategy. Is it? With the right subset. Is it? And then you go back, do the same thing. You need to find the new middle item. Is it? In the subset this time. Is it in the sub? Yeah, please.
Do we not also compare the search item with the high and low index, like when finding the middle?
Oh yeah. Very good suggestion. I forgot to mention that. Yeah, very good reminder. And of course, yeah, you needed to first compare the item with the middle one. Yeah, with the middle one. Very good reminder. Okay, very middle one. Is it? And if it is it? If it is the item, is it if middle one? Here the mid. So if middle one is the item, then we stop search. Is it? We find it. We stop search. Otherwise, if it is greater, then you drop half. Then you continue back with this strategy. And if it is less than, same thing. Okay. So if less than, then you continue with the strategy. Yeah, please.
No, I mean, like in the first example, you were looking for 10, and it was the very last index.
Yeah.
And so when you start your search, you find the first and the last index, right? To then locate the middle.
Yeah.
But if you just found, if you found index 0 and index 9, would you not compare those values as well since you already have them?
No. We don't do that. Yeah, that's maybe you can think about it. Let's see. The binary search algorithm don't do that. But you are right, that maybe you can improve this algorithm. Said, okay, anyway, you're going to do the first and the last. Yeah. So first and the last, is it index? Is it, and we have the middle index. Middle index. And right now the algorithm works is just compare the item with the middle. But you're right, because anyway you have the first and the last. Is it maybe we can also compare with first and last. That's basically, I think, is an improvement, maybe improvement, a small improvement for binary search. Yeah. So in researching, yeah,
I
yeah,
think
please.
Alex is talking about time complexity. It might be less efficient.
Over here, you're right. Yeah, we discuss time complexity. Yeah. Algorithm efficiency. Yeah. Yeah.
Well,
this
if
is,
our list.
Pardon me. Very good point. Who just bring that question? You can send your question to the chat. I will give you bonus point. That's a very good deep thinking. Yeah. So why don't we also compare first and last? Yeah. Please, next. Yeah, go ahead.
I guess I'm off topic, but I was just trying to mention that the time complexity of binary search is like log n,
yeah,
which is
yeah.
less than of linear search.
Yeah,
but the problem is that we have to sort a list.
Yeah,
and in that case, sometimes sorting a list can take a long time.
Yeah,
and
yeah.
linear search is more efficient.
Yeah, yeah. No, here, yeah. So that's a good perspective, is it? And here, I don't want to bring this time complexity, is because in CS3 we are going to learn the beginning of the time complexity discussion. Okay, and the major topic regarding the discussion of all sorts of algorithms. We have a class called CS265 Oct, okay, algorithm. That's over, in that class, we discuss systematically about all classical algorithm, their efficiency, okay. But all of your opinions are very, very valid and deep thinking ideas. Okay, so you're right. Yeah, so linear search, it's log, not log, it's n. We call it order of n search. So it's linear. For binary search, it's log n. Nature log n. Okay, so if you see, so over here we said this is the time to take, is it? And this is your data size. Data size, is it? With linear, it may be something looks like this, but with log, you can see with the data size grow, is it? The time you take won't grow as huge as linear, okay? And there are also some quadratic or power, then there's those, anyone comes with that kind of algorithm is least efficient, is it? Yeah. So, but very valid point. You see, okay, binary search, the precondition is sorted already, is it? And but just think about it. If our goal is not purely just for sorted, assuming like for assuming like in Amazon, is it? Amazon, so all of its database, the database items may be already sorted, is it? Anyway, because of their business requirement, is it? They store items assuming already sorted, or like our school's database. Is it like for students? Is it maybe they already sorted by student name or something? Is it? So anyway, that of those items already sorted. Then when you try to do search, you see, then if you use binary search, of course, it's better than linear search. Is it? That's why we still need binary search. Is it? It's just regarding search. Okay, we don't need to worry about sorted part. So when we discuss the algorithm efficiency here, we care about is search. Okay, we don't care about if it's sorting. Okay, so sorting later on, but not in this class. In CS3, we will also discuss different kinds of sorting algorithm. Okay, then you will also see there are various sorting algorithms. Okay, so anyway, binary search, as we discussed, the algorithm we all understand, but what is this related with recursion? Anyone can guess why it's related with recursion? It's because what?
Because we call it self, and we give different parameters. We give a, I guess, like a points, like the length of an array, like
very
to end, something like that.
Yeah, very good insight. Is it? Because you see, each time you apply the same strategy, is it? Same strategy again and again. Is it? But what? We reduce the search range. Is it? Same strategy, but the search range you reduced. Is it? So that's why we can use recursion. Okay, so let's see the method. Okay, so here is our recursive binary search method. Now you will understand this method. So over here, we said we are going to do with a list. Okay, oh, not list, with an array. Okay, this is an array. And the key is the item to search. Okay, and this is our first index for the search range. And this is the last index for search range. Okay, and then let's see. We said if your first index already beyond your last one, so that means like 10, is it? And suppose this is 9, is it? And so your 8. Okay, suppose we have some sub-range so the first already go beyond the last. So this may be your first. And this is your last. Is it? And this first already greater than your last. Is it? That definitely is not your search range. Is it your search range first? So over here it's low. Is it? Low should always less or equal than high. Index, okay, this is regarding index. And if it is greater, then definitely no. That's why you return a negative. So that means you didn't find it, didn't locate the item. The item is not in the search. Is it? So this is one of the stopping case. Stopping case, is it? And then what I did is, okay, I find the middle index. Is it? I take the integer part. And then I compare the item with the middle item. Is it? If the search item is less than, I just care about the left sub-range. Is it? I will ignore, so drop the right part. Right part. Is it? So that's how you won't change the array. You won't change the item. Is it? And the starting index for the range, you won't change. But did you see we reduce the case here?
I've got a question.
Yeah, please.
So why do, like we have a first if statement, low is bigger than high. Why do we return negative low -1? Like, what is that?
Okay. Oh, okay. So whatever this, yeah. So that's a very good question. Okay. So the return value for this method, okay, is the index of the item. So the item, you will locate where the item is with its index. That's what you are looking for. Okay,
And the first statement says that we didn't find an index, right?
Yeah, because it's a negative, and the index cannot be any negative value. Is it? Index
so we can return just -1, right?
Yeah, you can also do -1, whatever you want. Is it? You can use any negative value. Is it? Yeah.
Okay, makes sense.
Yeah. So it's anyway, index can only be a 0 and a positive number. Is it? So that's why. Okay, over here. So anyway, so here you update the high index. Is it to middle -1? Is it? So I did reduce the search range. Is it? You reduce. And yeah, if you find it, is it? If you find it, then you just return its index. That's a valid one. Is it? Otherwise, if the item you look for is greater than the middle one, did you see you update the search range? Is it? Update search range. Is it? With you update the middle, you keep the high part untouched. Is it? Intact. Is it? So that's how, and this is also stopping case. Is it? So here we have 2 stopping case. Is it? And 2 recursive case. 2 recursive case. Is it? Reduced case. Is it? Okay, so this is how recursive binary search works. Okay, and I remember someone mentioned, why don't we compare with the first and the last? Is it? So you can try that also. Okay, how do you modify this binary search with also the first and the last? Okay. Okay, so that's regarding binary search. And the last one is a very interesting one regarding binary search. Oh, where is, okay. The last one is called hanoi.
Towers of Hanoi.
Yeah, Towers of Hanoi. Yeah, very good. Towers of Hanoi. It's a game, okay. And this game, basically, if we don't apply recursive concepts, it's really hard to find a solution. So that explains why we need recursive, okay. So the idea is like this. So you have 3 packs. Okay, we call it pack A, or we call it pack source pack. And this is destination pack. This is a spare pack. Okay, then we have a bunch of plates, and they are not the same size. So they are piled from smaller to larger. That's how they piled. Okay, so over here I have a bunch of plates. Those are plates. And your goal is to what? You need to move the plates each time. Move one. Okay, you need to move all of the plates to the destination pack. But each time you can only move one. And when you move, you are not allowed to have bigger on top of smaller plate. So each time when you move, you cannot place a bigger plate on top of a smaller plate. You must have bigger one on the bottom of a smaller one. Okay, but you can use this spare pack. Okay, for the intermediate step. So then the idea is, how do we complete this game? Is it? So if we apply the recursive concept, okay, the idea is here total I have n plates, is it? And this is the top n minus 1 plates. I'm assuming, so you assume, okay, as to how, don't worry, you assume this top n minus 1 plates already moved to the spare one. You assuming it, okay? It's already here. Then you only have the largest one, is it? With a single step, you can get the largest one to the destination, is it? So at least you finish this largest one. Then further, your goal is, okay, now I can move the top n minus 2, is it? And my goal is to move this second largest one to the destination. So I can move the top n minus 2 to this one. Is it? This is the top n minus 2. So now this can be viewed as a spared pack. And this assuming it's a source. Is it? And this is still destination. You assuming, okay, this top n minus 2 already moved to the spare one, and this is one step. You get the second largest to the destination, is it? And the same thing with the n minus 2, then you can do, okay, n minus 3, is it? You move to this spare one, is it? And then the third largest can be moved to the destination pack, is it? So you keep doing something like this, is it? And then you backtrack how you complete each step. Then you will have all of the plates to be moved to the destination pack, okay? Following the rule of this game, okay? So anyway, so that's the idea. So here the whole concept is, you see, each time you reduce the case by 1 plate, is it? So that's the idea about this Towers of Hanoi game, is it? So let's see, we can mimic this, okay? The Towers of Hanoi. So we have n plates, is it? This is the source pack, is it? And the destination pack. Okay, and this is the spare one. The spare one, etc. And it's a character. Okay. Okay, so they will be identified by some character, etc. So let's see. Okay, if you only have a single plate, of course, you can just say, okay, move from source to destination. I output everything. So this is a stopping case. Stopping case. Otherwise, I first need to move what? Move top n-1. From source to what? To this time you use spare as destination. As destination. And the destination is treated as spare. I change because it's supposed to be source, destination, and spare. But you see, you swap. You swap the pack. So the idea is, okay, because you are going to move the top n-1. So this is the largest, So this is the top n-1, From source to spare. Source to spare. And of course, it involves the steps to do one by one move. You just assume it's move here. So that's why you can call this method itself with reduced case. With reduced case. And then you move what? Move the largest one. From the source to the destination, you can output it. But you are not done with the top n-1 yet. You still need to get all of them to the destination. That's why you still need another call. Move top n-1. From this time, you will treat spare as source. You treat, because your goal is to move this top n-1 from spare to destination. So you treat this as source. And this as destination, and the source is treated as destination. So if we write this kind of recursive method, then the output will tell you step by step how you move each plate. Okay, move each plate. Okay, so that's all of the recursive method. Okay, so I'm going to